Okay, so last time we were talking about length. Uh, so um, so this is what I defined to be length of a curve in this hyperbolic space. So today, okay, today I will also define distance. Yeah, okay, so distance and mm, okay, so this distance I defined, I claim that it is a metric on H. I will not prove it, but uh, you can prove it using some of the things I prove later on today. Okay. Um, I also defined geodesics to be this. So like a curve gamma will be called a geodesic if it is the length minimizing path. Okay. Note that this is so on a general Riemann manifold, geodesics will be defined in some other way. But for our case, this is an equivalent definition. Okay. So okay. So I claim that vertical lines are geodesics. That is, um, any lines like this. If you take 2 points on these lines, any 2 points, the distance between these 2 points is minimized by this path. So yeah, so that is what I mean by geodesic uh, proof. Mm, okay. Mm. So I'm taking 2 points, P1, P2, on some y equal to, sorry, x equal to x naught line. And I'm taking some curve. Uh, it could be anything like this. So, okay. So then length is given by, so by definition, this is the length. But since we know that x prime square is positive, um, not non-negative, we get this inequality. Which again gives us okay. This B and A are the coordinates B and A here. Okay. So what do we have for, so for any path gamma, we have length of gamma is greater than or equal to logarithm of B by A, right? Now if we find a path which achieves this length, then we would have found the geodesic, right? We would have found a geodesic. So if you consider the path gamma of t equal to I, so let me call this alpha. So alpha is just, it is just a path going this way. This is alpha. Okay. So if you do the computation for this, you'll get the length. You will get that length of alpha is logarithm of B by A. Hence, uh, okay. Okay. So by proving this, we have achieved two things. One is that we have proved these vertical lines. These are all geodesics. Other one is we have found distance between 2 points on vertical lines. Okay. So we can sort of get distance formulas for other points also using this. Um, okay. Just
Correct? Is it obvious that L gamma depends only on the image of the curve? I mean, not on the speed or anything.
it is not obvious, but if you do reparameterization, you will
Okay.
see by, like, if you do some change of variable thing, it will get cancelled and it will still be the same. Okay, so it basically depends on the image mostly.
Hmm.
Okay, is that clear or?
Yeah, yeah, yeah.
Okay, cool. Mm. Uh, Corollary, we have di. Mm. Okay, there is one other result you should know, which I will not prove. Uh, um, so the hyperbolic metric is complete. This can be proved by elementary methods, but there is also this theorem by Hopf-Renault, which relates like geodesics and completeness of a metric. You can use that also to do this. Of course, that is a difficult theorem on its own. Okay. Okay. Now we have talked about distances. Let us talk about isometries here. So given any diffeomorphism from H to H, if you look at this, if you look at this metric, and this is a metric if you interpret it rightly, if it happens to be equal to this original metric, then I will call this this diffeomorphism to be an isometry. Um, is it uh, is the meaning of this clear? Okay, anyway, you will see, like, okay, I'll do some examples, you will see. So given an example, so look at z plus a, where a is a real number. Then our we see that the metric is invariant if you compose with t. So t is, and okay, um, there are other examples as well. Okay, so these three will also be isometric. Um, Next, I will say that
Is lambda
so
greater than 0?
huh?
Lambda greater than 0 because we want it to be in hyperplane, in like upper plane.
Oh yeah, right, right. Wait. True. True. Okay. Okay. Now claim is we have been looking at Mobius transforms, which are PSL2R. We know that it acts on the upper half space as diffeomorphisms. Now, the reason we have been looking at it was because it is they form isometries of the upper half space. So um, if you look at T of Z, take any Mobius transform from PSL to R. Uh, so if you go through this calculation, you will see that these these Mobius transforms, they are isometric. Um, you can do it this way, or you can also say that okay, any T of Z can be written as a composition of these things, right? These things, and I guess this one also. So it can be written as composition of this, and when you compose isometries, you will get isometry. So you can argue that way as well. Okay. Okay. So now we have that our Mobius transforms are isometries. So we have at our disposal a huge set of functions which we can apply to make our calculations easier. Um, One other observation you should make is since this isometries preserve the Riemannian metric, they are supposed to preserve the distance I defined. So that will be preserved if I preserve length of curves also. So so you can prove this. So what I'm saying is if T is an isometry, then it preserves the length of curve. Okay.
Karthik, can you go a little bit up? Like where you wrote dt by dz. So what do you mean by dt by dz? Like
Uh,
how did you do that?
oh, sorry, this is not mod. Is this mod? This should not be mod. Sorry, sorry. This is not mod. This is just
Mm, I think that should be mod. Like, I don't know. Like, how did you
Um,
differentiate it, like T with respect to Z?
Let me see, just 1 second. So this will be A. So I just did like complex differentiation. That was what I wanted to do.
Okay.
So this, like, you have this here, you just differentiate it
Okay.
as a complex function.
Okay. Then yeah. Then it will be like, yeah. There's no mod.
Yeah, yeah,
Okay.
yeah. I think I missed there. Um, yeah, like this, doing this is not the correct way, because I am actually saying you are preserving the Riemannian metric. This is like a weird way to do this, but I don't want to use the language of pullbacks and other stuff here.
Okay. Okay.
So this is like a hack way to do it.
Okay. Okay. Fine.
Yeah, just like, if this doesn't make sense, just think of it as composing it with these functions here. So
Mm-hmm.
these functions are isometries, and so your
Yeah.
composition is also isometric. Okay. Okay. So uh, okay. So one, we have proved that vertical lines are geodesic. Other one we have proved is Mobius maps are also isometries here. So if you look at a vertical line and take its image under a Mobius transformation, whatever you get should also be a isometry. And we know that lines, Mobius transforms takes like circles in C infinity to circles in C infinity. In H2, what it means is a vertical line, will end up going to either a line or some kind of a circle. It is not just any random circle, it will be these kind of circles. So any vertical line, this will always end up going to either a vertical line, or it will end up going to circles like this, which, like, whose center is on the real line. Uh, okay. So why is it circles which are like at right angles to the real line? It is because, like, Mobius maps you see are like complex holomorphic maps also. Holomorphic maps, you can prove that they are conformal. That is, like, they will preserve angles. So basically your map will preserve this angle. So wherever this angle goes to, it has to be 90 degrees. So that is why it will end up going to circles orthogonal to the real line. Is this clear? So what we end up proving is, um, Okay, so what we ended up proving is all vertical lines and semicircles here, they are geodesic. Okay. Um, okay. One other fact is so there is a the claim is these are all the geodesics. Proving that is like that comes directly from Riemannian geometry where you solve some geodesic equations basically. So the reason why these are all the geodesics is um, if you have any point in your space and if you pick any tangent vector at this point, um, there is a theorem saying there is always a unique geodesic along this direction. So there is only one and only one geodesic. Um, so if for every direction we get one geodesic, then we have shown that those are all the geodesics. Okay, those will be all the geodesics. And using these circles and lines, you can show that for any tangent direction, you can get these things. So basically, that is why they will be all the geodesics. Okay. Okay. Cool. So till now we were doing the upper half space model. Now I'll just define one other model which will make some computations easier. This is the disk model. So okay, so we will take the unit disk in the complex plane and define this to be our Riemannian metric. Um, so you can verify that. Um, so verify that this map, which takes the upper half space to our unit disk, um, this is an isometry. So basically, so whatever we do right now will be up to things up to isometry. So for us, the upper half space and the disk model, they are equivalent. So we can jump from one to the other uh, without any troubles. So so what are the geodesics in this model? Uh, So geodesics here will be images of geodesics from the upper half space. Again, because of some angle preserving properties, you will see that they will all be either lines or circles, which are like perpendicular here. Perpendicular. Okay. So geodesics in this space will be these things. Okay. So again, using the metric, you can just calculate. So basically, this is the distance between the origin and this point. Okay. If you just, since you know that the geodesic is this, you can take a path and parameterize like this. Then if you integrate, you will get this logarithm. So you can notice that this metric here, this has rotational symmetry. What that means is if I rotate z to e to the power I theta times z, your metric will be invariant, which means rotations are isometries here. So you will have that you take your r and you turn it around. This will also be same as yeah. So what happened in this model is if you take 0 here and if you draw some circle, all the points on the circle are equidistant from the center point. Okay. So basically this is also, this looks like a Euclidean circle for us. In Euclidean metric, this is a circle, but in the hyperbolic metric also it is a circle, but it has different radius. So in the Euclidean sense, it has okay. So this is the first time we cannot what so here you see that like Euclidean sense, even though the radiuses are, your hyperbolic sense, it is different. It is important to note this difference because it might get confusing at some point. Okay. Mm. So from this we get that Okay, so if you define your hyperbolic ball centered around 0 of radius, not radius r. So if you look at a hyperbolic ball of this radius, as a set, it will be equal to so this hyperbolic ball is as a set is actually equal to just this Euclidean ball. Okay. Okay. So using this, you can prove that. So using this, you can prove that the topology induced by this new metric is actually same as the original metric. So this is, you can prove this by, what do you want to prove? First of all, if you take a Euclidean ball and a point inside that Euclidean ball, you need to find a hyperbolic ball inside it, right? Again, you can use that Mobius transforms takes disks to disks and do some kind of argument there to get these. You can do the other way also, like inside a hyperbolic ball, you can find a Euclidean ball. So that is why how you'll get the compatibility. Um, so if you define rho to be the distance between 0 and the point r, you can get that r can be hyperbolic tan of rho by 2. So you can use this to find points at a certain distance. Say like you want to find a point at a distance, you want to find a point such that distance from 0 and p is rho, then you know that p will be equal to tan h of rho by 2. This is on the real line. Okay, just a side note. Okay, we know that circumference you can also, since we saw that like a hyperbolic ball is also actually a circle, you can parameterize it and you can calculate the circumference. So Okay, so if you take a hyperbolic ball centered at 0 of radius beta, and if you integrate the circumference, you will get it to be equal to sine hyperbolic beta. But notice that so in the Euclidean space, if you take a ball of radius beta, the circumference will be 2 pi beta, right? So you notice the difference here that as beta grows, for the Euclidean case, our circumference goes linearly. But in the hyperbolic case, it grows. So this is sort of an exponential. So in hyperbolic space, this circumference grows exponentially. So this is an important fact because this is actually capturing what we call as curvature. So one way of thinking curvature is, so so positive curvature is just, think of positive or zero curvature to be just your Euclidean space. And if you will say some space has negative curvature, if in some sense there is more area as you move out from a point. So here you are seeing that you start at a point and you move out, your radius of your circumference of the circle as you move out is growing exponentially, whereas in your normal sense it is linear. If your curvature was positive, your growth will be sublinear. It will be some kind of a sine or a cosine here. So it won't even be linear. It will like grow and come back. So this okay, like this is just words which I'm saying, but there is also a way to make it rigorous by saying some derivative of the circumference will be equal to the curvature. Okay, but I will not do that now. Yeah, I guess, okay, I think I'll stop here today. Are there any questions?
So yes, what Chinmay was saying that the equals to 0 when they are same points, the distance, and it is greater than 0 when they are different points. So is there any possibility that we can take two arbitrary points and bring them in a vertical line without changing the distance?
Yeah, that is what, exactly, that is what you will do. Like you will take some two arbitrary points, find some Mobius transform so that they become vertical.
Okay.
And on
then we have
vertical
proved
lines, you know
something
that
geodesics.
Yeah, like on vertical lines, you know that two different points will have non-zero distance between them.
So what we have proved that the vertical lines are geodesics, we haven't used the fact that the distance is a metric, right?
No, you haven't.
We haven't. So we can use that thing.
Yeah, like geodesics. Yeah, we haven't used it. Yeah, you can. Yeah. Also, geodesics, it's just some integral calculations, right? Like we have used nothing there.
Yeah.
Any other question?
क्वेश्चन नहीं है, पर एक वो जो अप्रोक्सीमेशन का हम बोल रहे थे,
हाँ,
वो शायद स्टोन वायरस्ट्रास से हो सकता है, मुझे लगता है.
स्टोन वायरस्ट्रास में कंटिन्यूअस फंक्शंस मिलता है ना.
हाँ, तो कंटिन्यूअस को स्मूथ से अप्रोक्सीमेट कर सकते हैं भाई.
हाँ, वही. हाँ मैं वही सोच रहा था कि मतलब ऐसा होना ही चाहिए. इट्स आई
हाँ
जस्ट
हाँ
नो एग्जैक्टली.
कॉन्टेक्स्ट क्या है, कौन सा अप्रोक्सीमेशन की बात कर रहे हैं?
तो मैं इनिशियली बोला था कि यू कैन मतलब डेफिनेशन में आई सेड यू हैव टू टेक स्मूथ और यू कैन टेक पीस वाइज स्मूथ आल्सो
ओके ओके
when I was defining the infimum, but it happens to be same because कुछ approximation करने के बाद मतलब मिल जाता है, मतलब they will become
हाँ
equivalent.
ओके